Today we discuss about logistic growth. This is the third episode on population dynamics. So in our last episode we have seen that the exponential growth equation is n is equals to n0 e to the power rt. So this simple exponential growth equation can serve us well for short time horizon or with constant birth and death rates and age structure, and there is no immigration or emigration under specific environment condition. অর্থাৎ simple exponential growth কার্ভটা বা গ্রোথ ইকুয়েশনটা খুব অল্প সময়ের জন্য ঠিক হবে, অথবা ধরা যাক যে আমাদের বার্থ রেট, ডেথ রেট এবং এজ স্ট্রাকচারটা কনস্ট্যান্ট ফিক্সড এবং বাইরে থেকে কেউ আসবেও না, এখান থেকে কেউ বাইরেও যাবে না, এরকম কন্ডিশনের জন্যই এই এক্সপোনেনশিয়াল গ্রোথ ইকুয়েশন দ্যাট ইজ n is equal to n0 e to the power rt তার সঠিক হবে। ফর এক্সাম্পল আমরা যদি দেখি যে 2012 এ সাপোজ ইন 2012 population of a country was 14 million and rate of birth and death were during the period that is in 2012 is 0.028 and 0.008 respectively. Now we have to estimate the present number that is in 2022 using exponential growth equation. তো এখানে বলে দিয়েছে exponential equation দিয়ে করতে হবে। তো এখান থেকে আমরা n0 আমরা জেনে গেছি যে it is 14 million and E is constant, T is 10 years, 22 minus 12 that is 10 years, and we have to identify find out the value of R. R হচ্ছে কি natality minus mortality, that is 0.028 minus 0.008, so this is the R. So by using this number we can find out that the population in 2022 will be 17 million. So this is absurd in in nature, because it does not occur in nature, and for most of the population even small growth rates cannot continue for long before environmental constant limit further increases. এনভায়রনমেন্টের যে লিমিটগুলো রয়েছে, যে কনস্ট্যান্টস গুলো রয়েছে, সেগুলো যদি আমাদেরকে না বাড়ানো হয় তাহলে এইভাবে কোনো ইকুয়েশন হতে পারে না যে 10 বছর ধরে তাদের বার্থ রেট, ডেথ রেট সমান হবে। ইকোসিস্টেমে কোনো সেভারেল ইমিগ্রেশনের প্রশ্ন থাকবে। সো ইন অ্যান ইকোসিস্টেম আদার স্পিসিস প্রেজেন্ট এ ভ্যারাইটি অফ অ্যাবায়োটিক conditions etc. act in a way that a given population will have an upper size limit and cannot be exceeded. So in such limit is called carrying capacity of the environment for the population, and carrying capacity is denoted as K, and carrying capacity is determined by the availability resource as food and space. So now we discuss about the typical curve for a bacterial population. So this is the curve. So this curve illustrates some of the complexity that natural biological system often exhibits. So there is 4 phases of this curve and divided into 4 phases. It is lag, exponential, stationary and death phase. So lag phase, when the bacteria are first inoculated into a fresh medium, so a little or no growth follows, corresponds to an initial period of time. So in this phase bacteria adjust themselves to their new environment, though population remains temporarily unchanged, but this does not mean that the cells are dormant or quiescent. On the contrary, during this stage the individual cell increase in size beyond their normal dimension. Physiologically, they are very active, synthesizing new protoplasm enzymes, coenzymes, which may be deficient in the new environment. So then there is an exponential growth that is called log phase also, that after bacteria have adjusted to their new environment, a period of rapid growth will follow. So during this time, conditions are optimal and population doubles with great regularity. So then come to the stationary stage. As food supply begins to be depleted or as toxic metabolic products accumulate, the population enters no growth. তো এখানে হয়তো ফুড সাপ্লাই কমে গেছে বা টক্সিক মেটাবলিক প্রোডাক্টস তৈরি হয়েছে, সো সেটা গ্রোথকে ইনহিবিট করছে, সো এখানে স্টেশনারি ফেজ দেখা যাচ্ছে। and at the end, as the environment become more and more hostile, population gets start decline. So this is the typical growth curve. Now we discuss about the logistic growth. So population projection are often mathematically modeled with logistic or S-shaped, sigmoid shaped growth curve, which is called sigmoid shaped curve. It suggests that an early exponential growth phase while conditions are optimal, and followed by slower and slower growth rate as the population nears the carrying capacity. So this is the carrying capacity. So when the population N reaches near the carrying capacity, so the growth curves becomes flattens. So mathematically, logistic growth curves is derived from the following differential equation, that is dn dt is equal to Rn into n minus 1 minus n by k. So here n is the population size, k is carrying capacity, and R is the exponential growth rate that would apply if the population size is far below of the carrying capacity. Here the most important thing is what is R. In exponential growth, this is the R is one thing, and in logistic growth R is something different. In exponential growth rate, R is a constant when n is equals to 0, that is population is 0. When population size is 0, then the value of R is constant and the single value, so this is right for the exponential growth. But when the population is much less than carrying capacity, that is when n is very less with respect to k, then this fraction is will be negligible, and so 1 minus that will be 1. So the equation will be dn dt is equal to Rn. So when the population is much less than carrying capacity, population growth can be modeled with the rate constant R without significant error. So তখন এটাকে ইউজ করা যেতে পারে। কিন্তু যখন when n increases এবং n increase করতে করতে একটা সময় reaches carrying capacity তে পৌঁছে যাবে, তখন কিন্তু আমরা দেখতে পাবো যে when n is equals to k, তো তখন এই অংশটা হয়ে যাবে 1, that is 1 minus 1 is equal to 0, so dn dt is equals to 0, that is no change of growth is occur with respect to time. That's why this portion is become flat. So from here we know that 1 minus n by k is the environmental resistance factor. So this is called environmental resistance. So as population growth, the resistance of further population growth continuously increases. The resistance to further population growth continuously increases. তো এই n যখনই বাড়বে তখনই আমাদের পপুলেশন গ্রোথটা কমতে থাকবে, তাই আস্তে আস্তে কার্ভটা এস এর শেপ নিয়েছে। তো আমরা এখানে ওই জিনিসটাই আরেকবার একটু আলোচনা করে নিচ্ছি যে rate constant r. It is pertinent to mention here that the exponential rate constant r is known as intrinsic rate constant of natural increase for a particular logistic growth curve has a single value correspond to the exponential growth that occurs only when n is equals to 0. That is, when population is 0, then the value of r, which will be the single value, as I told earlier, will be the value of r, and this is called exponential rate constant. But when the growth rate, the population growth rate is measured at time equals to t, that doesn't mean that the n is equal to 0, but it doesn't mean it is not necessary that n is very less than k. So this is called instantaneous rate constant, that is represented by r0. So when r0, that means the measurement of rate constant at t is equals to 0, but when r small r is used, that means the measurement of r is done when population is equals to 0. That means the two rate constants for growth rate are not same. R is the intrinsic rate constant for a particular logistic growth curve as shown above, and R0 is the provisional rate constant for the instantaneous growth rate at any time if growth is assumed to be exponential and not logistic. একটা এক্সাম্পল দিলে আমরা এটা বুঝবো যে আমরা ধরে নিচ্ছি যে পপুলেশনের ক্যারিং ক্যাপাসিটি হচ্ছে কে ফরে এবং তার জন্য সাফিসিয়েন্ট রিসোর্স রয়েছে। তো সাফিসিয়েন্ট রিসোর্স রয়েছে ফর কে পপুলেশন, সো কে ইজ দ্য ক্যারিং ক্যাপাসিটি, and at present n is the population size, and it is said that n is very less than k, and r is the growth rate constant, that is when n is equals to 0, then r, and the population, that is population size, when population size is 0, then n is equals to 0. So when all individuals are identical, each individual uses 1 by k of resource, and when and reduces the maximum growth rate r by 1 by k, and thus n individual reduces k by n by k. So relationship between r0 and r is expressed as r0 is equal to r into 1 minus n by k. এটাকে একটা এক্সাম্পল দিয়ে যদি আমরা দেখাই, যে ধরে নিই যে ক্যারিং ক্যাপাসিটি হচ্ছে 100 এবং এই মুহূর্তে ইন্ডিভিজুয়ালস রয়েছে 10, তাহলে আমাদের কাছে যে রিমেইনিং রিসোর্স রয়েছে দ্যাট ক্যান সাপোর্ট আপ টু 90 ইন্ডিভিজুয়ালস. So the proportion of remaining resource will be 1 minus n by k, and that will be 0.9. So when r is equals to 1, অর্থাৎ when n is equals to 0, then r is equals to 1. When r is equals to 1, n is equals to, and when n is equals to 10, the growth rate r will be changed to 0.9, and when n is equals to 90, the growth rate r will be the 0.1, and so on. So r is the the constant when n is equals to 0, but r0 is the constant when t is equals to 0. That is, in different time the value of r0 is changed. So this is the relation between r0 and small r. So in logistic growth we use this portion, that this r as r. So you can see that in logistic growth equation we replaced this r or r0 whatever in exponential growth rate is by this r into 1 minus n by k. So this will be our logistic growth equation. It derived from this exponential equation like that, and we can multiply this and we will get this formula, that is dn dt is equal to Rn minus R into n square by k. So from here we get two equivalent forms, that is dn dt is equal to Rn into 1 minus n by k or dn dt is equal to Rn into k minus n by k. তো আমাদের যে সমস্ত প্রবলেম সলিউশন আসবে আমরা এই দুটো ফর্মের উপরে বেস করে সেগুলো সলভ করতে পারবো, এবং এখান থেকে আমরা যদি আলটিমেটলি পপুলেশন এট টাইম টি কে বের করতে চাই তো উই ইউজ nt is equal to k by 1 plus e to the power minus rt. সো এই ইকুয়েশনটা কিভাবে ডিরাইভড হলো সেটা জানতে হলে আমি পাশে করে দিয়েছি সলভটা, যে dn dt rt থেকে আমরা যেটা পেলাম এখানে nt is equal to n0 into r e to the power rt, সেখানে r replaced by this so and then derivative with integration next we taking a natural log from both sides, and ultimately we reached this n is equal to k by 1 plus e to the power rt. So thank you for watching this video.